Hello, I'm Mike McCulloch. Today I'd like to try and explain in a simple way how inertia works. So why is it that when you move your hand around, you feel a certain resistance to that movement? Your hand feels heavy. So in order to understand this in terms of quantized inertia, we have to first consider an object that has no acceleration, which is not actually possible in quantized inertia. Everything has to have an acceleration above a minimum acceleration. But if we start from this scenario, then this will help to explain it. So here we have a diagram of the entire cosmos with us in the center. Now, there is a cosmic horizon which surrounds us on all sides and is symmetric. So this would be a sphere, a cosmic sphere surrounding us, and we can work out the size of this, because this sphere will be the extent of the entire universe that we don't know about, the extent of that we could have received information from in the time that our part of the universe has been in existence. So in what follows, I'm going to assume that the age of the universe is about 4 times 10 to the 17 seconds, about 13-14 billion years, which is an assumption, but at least I'm stating it. So in order to work out how far we could have received information in this time, we multiply this age by the speed of light, which is the maximum speed of transfer of information. So we get 4 times 10 to the 17 times 3 times 10 to the 8, speed of light, which gives us about 10 to the 26 meters. And this is widely assumed to be about the size of the universe. So we have this universe, and there are quantum waves within it, but it doesn't really matter that there are quantum waves, because the distance to the horizon is the same in all directions. So these quantum waves, however many of them there may be, and no matter what wavelength they will be all the same. They will be coming from all directions with the same intensity. So this is rather like the stained glass window in a cathedral, or any window for that matter. The forces on it are huge, 10 to the 5 pascals. But the point is that the forces are exactly balanced. So the window is being pushed from outside just as it is being pushed from inside by these huge forces, and they cancel almost exactly. So the window doesn't break. But now, if we go back to our universe and we suddenly break the symmetry by we're on a spaceship, we accelerate to the right, as you can see here. So we're now accelerating to the right. Now something happens to break the symmetry. We get a Rindler horizon behind us, because it's slightly more difficult for information to get to us from the left-hand side than the right-hand side. So you can see the Rindler horizon forming here. And the distance to this is c squared over the acceleration, our acceleration caused by a rocket or whatever method we're using. Now, if you look at the quantum waves, without getting into it in any detail, if you look at the quantum waves, more of them can exist on the right of us. So I've tried to show that with the squiggles here. Than can exist on the left of us. So some of these waves will be disallowed by this new Rindler horizon. So now the situation is no longer symmetric. The pressure on the window is no longer symmetric, so it's going to break. Or in this case, we're going to get a force which will push us back towards the left, because there are more waves on the right pushing us than there are waves on the left pushing us. So we'll be pushed back. And I've managed to show with quantized inertia that this sort of model predicts inertial mass exactly, but with a tiny modification that enables us to model galaxies without dark matter and to produce thrust by doing this deliberately, by deliberately destroying the balance in the unradiation in these quantum waves. Okay, so this is an explanation all based on the age, which is an assumption. So this all holds together, providing this age is correct. But how do we determine the age? Well, that is another question, and it leads to quite a lot of argument about how sure we can be about that, and how the theory itself determines what the age would be. Okay, so I hope you've enjoyed this short, and I look forward to seeing you tomorrow. Goodbye.